We left off having motivated the search for some kind of master property which would say what is the desired security of a symmetric encryption scheme. And this property should be something that, if met, would imply a host of other nice things, effectively saying that really no partial information about plain text is revealed by ciphertext. And this property will be called IND-CPA. And now we're going to say how it works. Before we actually get into that, it may be again worth seeing how what sounds like something maybe technical and theoretical arises quite commonly in usage and in choices made by developers. So again, we can look at Stack Exchange, where someone is asking about what IND-CPA is, trying to check their understanding of it. And you see people kindly replying to that. And one of them even says that, no, you don't actually have it right. These are the kind of things that you'll understand and be able to even answer as you finish the class. Okay, so the highest level intuition for what IND-CPA is may be said as that the voting example we had is in some sense the worst case. At least a slight generalization of it represents the most stringent requirement for encryption. And once you have that, other things will be okay. So if you can follow this intuition, it will effectively tell you whatever you need to know so that the games and formalization that later follow will be made much simpler. So we consider a scenario where the sender is encrypting messages under its key K, which the decryptor knows, but the adversary doesn't know. And under the same fixed key, there's going to be a bunch of messages encrypted, say Q of them, where Q could be anything from 1 to many billions. So there's in fact a stream of messages being encrypted. Now, I'm going to assume for some reason that there are only two choices of that stream. The first choice is the messages here. So M0, 1 through M0Q. Okay, some Q messages. These messages should be regarded as known. The adversary knows what they are. There is another possible choice. These are the M1 messages. The sender is going to either encrypt all of these one by one or all of these one by one. Okay. The only thing the adversary has to do is figure out which of those two cases happened. Did the sender encrypt this stream or did it encrypt this stream? Of course, it does that given the ciphertext. The sender will pick one of the two streams, produce the ciphertext, and then ask the adversary, well, which stream did I pick? You know the messages in the two streams, you just don't know which of the two was chosen. If the adversary succeeds in saying which of the two streams was chosen, it wins, and we declare our encryption scheme to be bad. If the adversary throws up his hands and says, from the ciphertext, I really don't have a clue which stream you encrypted, then that's good, and we are saying our encryption scheme is secure. As if it wasn't enough that already the adversary is given the two streams and is able to restrict users to a setting where only one of those two streams is encrypted, not something else, will give it even more power. It can not only know, but it can pick the messages in these streams. Moreover, it can pick them adaptively. That means that it can pick this pair, get back the encryption of one of them, and based on that ciphertext, pick the next pair. Okay. Now, one thing we do insist is that the pair of messages at any index is the same length in both streams. So if you take, say, the third message in stream 0 and in stream 1, the messages themselves may be different, but their lengths have to be the same. And this is just because we are not able to hide lengths. Okay, so now let's go on to the formal definition. So the setup is that we have fixed a symmetric encryption scheme. So all its three algorithms, key generation, encryption, decryption. Remember the scheme and these algorithms are regarded as entirely public. Everyone knows these descriptions. The adversary knows them. You can assume you have code and software to implement everything in the scheme. Our goal is to measure the security of the scheme or to give a metric for that security. And as usual, we'll consider games. And just like for PRFs, there's a left and a right game, but they work a little differently. The two games actually differ very, very slightly. Both games have an initialized procedure, and it simply runs this algorithm to get a key K. This algorithm being randomized, this key will have some distribution. Once the algorithm is run and this key is produced, it's fixed for the rest of the game. And that happens in both cases. Both games export a procedure whose name is LR. That stands for left or right. The procedure takes input two messages, not one message, required to have the same length. The difference between the games is simply that here the left message is encrypted and here the right, and then in both cases the ciphertext is returned. The adversary is saying this is a message from the left stream, this is a message from the right stream. Encrypt whichever one you want. That'll depend on the game. This one will encrypt for the left stream, this one is going to encrypt for the right stream. Encryption is done using this algorithm and this key, and those are unchanged across all the different encryptions that could happen here. This indicates that randomization is present, possibly in the encryption algorithm. There are multiple queries allowed to procedure LR, but again, all are answered with the same key and the same E. Okay, now we take our adversary and we can run it. It can play either of these games. The same adversary can be executed with either game because the exported interface is identical. If you run that adversary, it's trying to figure out whether it's in game left or right. And so it'll output a 1 if it thinks it's in game right and a 0 if it thinks it's in game left. And we are interested in how well it does at predicting correctly which game was being played. So since there's randomization all over here, and possibly inside the adversary, whether the adversary outputs 1 or not is not something fixed, but there's a certain probability it happens. This is the probability that the adversary outputs 1 in the left game, and this the probability that the same adversary outputs 1 in the right game. Okay. We will usually be able to compute these probabilities from a description of the adversary and the scheme. Now, we're not interested in the magnitude of these, we're interested in how close they are. The adversary is outputting 1 to say, I think I'm in the right world. Suppose that in this case, it outputs 1 with a probability that's very close to this. That tells us that this adversary is pretty clueless. It's claiming that it's world 1 just as often when it's not true as when it's true. That is all captured in the definition of the advantage. The superscript is the name of the metric. It stands for indistinguishability under chosen plain text attack. The subscript is the scheme because we're measuring security of this scheme. The argument is the adversary. The advantage then is defined as the difference between these probabilities. So the probability of returning 1 in the right world minus the probability of returning 1 in the left world. Okay, now these slides are important and they have some amount of depth in them. It takes some time to look at these games and think about how they're running and what they mean and kind of understand these metrics. So this is the place where time and effort will pay off. Some caveats. Whenever an adversary makes a query to the left or right oracle, remember it can submit two messages, M0 and M1. They are required to have the same length. So they're bit strings and they have the same length. If an adversary that, say, you write in pseudocode in some assignment submits an LR query that consists of messages of different lengths, that adversary will just be considered invalid. What this captures in terms of security and privacy is that encryption is not trying to hide the length of messages, but beyond that, it kind of hides everything else. To map it back to our intuition, there are multiple left or right queries involved. If you consider across some queue such queries, all the messages sent on the left half, that is our first stream. All the messages put here are the second stream. We interpret this advantage somewhat application dependent way or subjectively to think about what conclusion to draw about the scheme. When that advantage for some adversary is close to 1, it means the adversary is doing well, and at least as long as the adversary is also practical in terms of resources, we can use that to conclude that the encryption scheme is bad. It fails to be IND-CPA secure. If the adversary advantage is close to 0, or by convention negative, then the adversary is doing poorly, and we can conclude that this symmetric encryption scheme is at least so far looking good. It doesn't mean it's secure, because maybe some other adversary would do really well, but at least it's resisting whatever attack this particular adversary is mounting. Security always depends on adversary resources. If you allow the adversary more computing time, more queries to its left or right oracle, it will do better. And the way we get security in practice is by setting parameters and picking schemes so that the resources T and Q needed to get a high advantage are prohibitively large. So we call a scheme IND-CPA secure informally if this advantage is small. We don't formally define what small is. It's a kind of context-dependent thing. And that should be true for any adversary that uses a practical amount of resources. We cannot restrict adversary strategies. They can be as clever as they like, but we can restrict their resources because in practice, they just don't have that much computing time. It's often easier to talk about insecurity. That means that given the scheme, you were able to exhibit as an explicit attack or adversary, which didn't use much in the way of resources, but got a very high advantage. And that's often what you'll do in exercises. We had determined earlier that electronic codebook mode is insecure, and illustrated that by an example in the application of voting. That conclusion is correct. What we'd like to do here is to see whether the formal definition we've given is consistent with that conclusion. In other words, now that we have this definition and abstraction, can we revisit electronic codebook mode and give an attack inside our model, inside this IND-CPA framework, that is an adversary playing these games that gets a high advantage? If we fail to do that, it doesn't mean ECB is good. Rather, it means our definition is bad. So you can think of this as kind of a test of the definition. It better capture what we've already understood to be true for ECB. So let's go back to ECB. We have our block cipher E, k-bit keys, n-bit blocks. And the way encryption is defined is it just applies the block cipher with the key to each block individually. So the encryption under K of M is this sequence over here, and there's no randomization. Given any scheme, you will often be asked a question like, assess whether it's IND-CPA secure or not. So what you're being asked is, can you design an adversary A and compute its advantage in these games? And this advantage should be high, very close to 1 or equal to 1. And also the adversary should have low resources, should be quite practical. And if you can do that, you will have shown that the scheme is insecure under IND-CPA. So let's see if we can do this. We expect we can, otherwise somehow what was the point of this definition? But it's good to actually see how we translate the intuition of the prior informal attack into a formal attack in our model, and it'll allow us to exercise the formalism. Whenever you begin this type of attack exercise, you start with intuition. So the first thing you need is you examine the scheme and you look for some sort of weakness, something that would enable you to tell which of two messages is being encrypted. In the case of ECB, of course, we already know what that is. We know that the weakness is simply determinism. If two messages are equal, well, so are their ciphertexts. And we now see that that's going to be enough to violate IND-CPA. When you have to show violation of some property like IND-CPA, and you have to give an adversary, you give this adversary in code, either Python code or pseudocode like I've written here or whatever, and it has to obey the correct syntax. It's a program, it had better compile. Compile means that it calls procedures it's allowed to call, and it doesn't use variables or objects that are not defined in its context and so forth. So our adversary has to call the left or right oracle. It can do that multiple times, and it's going to use that to figure out whether behind the left or right oracle is the left game or the right game. Is the left message being encrypted or the right? Remember, we're not doing this in general. We know what the encryption scheme is. It's ECB, and so it's written above over here. So how could you do this? Well, remember the weakness is that twice encrypting the same message gives you the same ciphertext. How is that captured over here? The adversary makes two queries. For the left message, it changes the message across the two queries. A 0 here and a 1 here. For the right message, it doesn't. It leaves it the same, a 0 here and a 0 here. In the right world, you'll get an encryption of a 0 and an encryption of a 1. In the left world. In the right world, you'll get encryption of a 0 and an encryption of a 0. So, since in the latter case, you'll get back the same thing due to the way ECB works, you simply test. If the ciphertexts coming back are the same, you know you're in the right world. If they're not, you're in the left world. Now this is exactly the same attack effectively as in our voting example. It's just been formalized in this IND-CPA framework. Since this is the first one we look at, let's go in detail through the analysis. So having written the adversary, I want to know what is its advantage. That means I have to figure out the probability that the adversary returns 1 in the right game, then figure it out in the left game and subtract them. So we write down here the right game. We know now that this encryption is done in this way. Again, maybe a little confusing to see two E's, but the script E is electronic codebook mode, which will coincide with the block cipher E when the message is 1 block long. Since these messages are 1 block long, it does so coincide. So whether here I write, at least for this particular attack, the script T or the other one wouldn't actually matter. So we now have the game. Let's look at when the adversary returns 1. It needs these two ciphertexts to be equal. What are the two ciphertexts? Well, there will be, this one will be encryption of 0, this will be the encryption of 1. Sorry, again, I'm juxtaposing. I'm looking at the right game. So encryption of 0 and encryption of 0. So block cipher applied to 0 and to 0, all with the same key. Obviously, these two things are the same since E is deterministic. So C1 will equal C2, and the adversary will always return a 1. So the probability it does that is 1. We move to the left game. We have not changed the adversary. It's identical. However, here now, the message that's encrypted is M0. That's the only difference from the right game. We want to assess when the adversary returns 1. The code is the same. So again, the question is, does C1 equal C2? So we look at what are C1 and C2. C1, since we're in the left game, is an encryption of 0. C2 is an encryption of 1. These encryptions, since the messages are 1 block, simply consist of applications of the block cipher with the fixed key K. Since the block cipher is a permutation, EK of 0 and EK of 1 cannot possibly be the same. So we get that this equality is never true. So the adversary will never return a 1. It'll always return a 0. So the probability of returning 1 is actually 0. You get the advantage by subtracting them. So for this adversary over here, the advantage will be 1. Furthermore, it's very efficient, almost no computation cost, and 2 queries to the oracle. So we have very blatantly violated the security of ECB and can easily conclude that it's not IND-CPA secure. And you can see many other such examples. Here's a generalization. What it says is that you show that the prior weakness is not just for electronic codebook mode, but happens whenever the encryption algorithm is deterministic. And this is a good conclusion to remember. If you have a deterministic encryption algorithm, you're not going to get IND-CPA security. So if you have a scheme where the algorithm is deterministic or you're designing something, you beware of that. This exercise is a little more interesting. It's also giving you some mode of operation, but this one is randomized. There's some randomization in the encryption, and it does stuff that has the flavor of counter mode somewhere in it. But nonetheless, the exercise concludes by saying that you have to give an attack showing that IND-CPA security is validated. You also have to specify how to decrypt by giving a little piece of code to do that. So we've now seen the definition, which my claim is kind of what we had earlier asked for as a master property. In other words, this is the desired end property we want from a symmetric encryption scheme. If it has that property, our expectation is that pretty much most applications will end up being secure with this scheme. And if you don't have that property, there will be some that aren't. And so that's the right goal for standards and designs and things like that. However, that this is true may not be entirely clear. So for example, we had earlier said that there are multiple properties in which we're interested. For example, if you encrypt messages M1 and M2 using some key K and with some encryption scheme E, I want that the adversary not be able to recover one of the messages, but also that it not be able to get, say, the first bit of one of the messages, or even the XOR of the bits of the first 2 messages, and so forth. But that isn't what our definition said. Our definition was this IND-CPA thing with the left or right games. So what about all these properties? Well, the answer to that is just that the IND-CPA property simply implies all of these. In other words, if it were possible for an adversary to, for example, get the first bit of a message from the ciphertext, that would translate to an attack under which IND-CPA is violated, and the same for the other properties. Now again, in a graduate class, I might illustrate that with a proof, but here it's just left either as a fact for you to know or something you can play with. And the intuition is that if you hand me a way to discover the first bit of a plain text from its ciphertext, I can quite easily turn that into an adversary violating IND-CPA by making a choice of messages sent to the left or right oracle, which, for example, differ in that first message bit. Now that we have a security metric, IND-CPA, we're in a much better position to go back to schemes and start asking, do they work? Are they actually secure? We know now that what we mean by secure is, do they meet IND-CPA? We've already ruled out ECB, but we have CBC and counter mode, and we'd like them to work. So to what extent do they work? It turns out that even with these schemes, there are non-trivial attacks. If our parameters are set appropriately, meaning our block ciphers are chosen appropriately, These are not necessarily damaging in practice, but if they're not, then they can be. And we'll now illustrate an attack on counter mode, which violates IND-CPA. Effectively, that means it violates privacy. And this is not merely theoretical. This attack was used to discover information about packets encrypted in TLS and was one of the reasons why triple DES was retired. So let E be our family of functions. Remember, counter mode is okay with a family of functions that may or may not be a block cipher. And we fix SC to be the corresponding counter mode symmetric encryption scheme. Here, I'm just going to try to illustrate first the idea behind the attack, which is also interesting in seeing how the birthday phenomenon is useful to violate privacy. So assume that we are encrypting messages just one block long. We have two messages M0 and M1, and effectively our adversary is just trying to figure out whether they're equal or not. So encrypt M0, you get some ciphertext. Remember that ciphertext is 2 blocks long. And encrypt M1, you get some other 2 block ciphertext. How is it done? Through counter mode, and we know how that works. It picks this at random, then starts this sequence, applies the block cipher or family of functions, gets this pad, XORs the message. Since the messages are 1 block long, this is all there is, otherwise there'll be more stuff here. And analogous stuff happens over here. Now, in general, looking at these ciphertexts, our adversary is going to be pretty clueless because most likely, regardless of whether M0 equals M1 or not, these ciphertexts will just be different. But suppose that the adversary got lucky. Well, what does lucky mean? We define it to mean that somehow the 2 random choices made here and here were the same. This could happen. They are random choices. There's some probability, perhaps quite low, that they end up being identical. But suppose it happens and our adversary then gets excited because now it can figure stuff out. In what way does it do that? Well, if these 2 are equal, then these starting points are equal. So these pads are equal. If these pads are equal, then if M0 and M1 are the same, we will have C01 and C11 be the same. And if M0 and M1 are different, these 2 second blocks will also be different. So testing equality of the second blocks of the ciphertext is equivalent to testing equality of the messages. So the second blocks of the ciphertext are in fact leaking equality. And this means you have violated IND-CPA security. Of course, there's a caveat, which is this only happens if you get lucky, which is very unlikely, you would think. But that's where the birthday paradox comes in. What the birthday paradox says is that actually it's not that unlikely. And that's because we're encrypting lots of messages. So let's see now how the actual attack works. So we have n as the input size for the family of functions or the input length of the block cipher. And we'll let q be some parameter smaller than 2 to the n, which is the number of messages that are going to get encrypted. And we'll let this notation here denote the integer I encoded as a string of L bits. Now L is the output length of our family of functions, but if you want to keep things simple and imagine we have a block cipher, just think L and N are the same. So what does the attack do? It asks for the encryptions of various messages where in the IND-CPA setting, so you have access to a left or right oracle. What our attacker does is that it always sets the right message to 0. Across all these Q queries, think of Q here as being pretty big, the right message never changes. But the left message is always different. It's a counter value, 1, 2, 3, 4 across the different queries. What is the point of doing this? Well, if equality is leaked and you determine that 2 messages being encrypted are the same, you must be in the right world, because in the left world that just never happens. Okay, in any case, so you call your oracle on these pair of messages and you get back a ciphertext. Remember, the ciphertext has 2 blocks, but you're doing this q times, so you're getting back q such ciphertext. Now what this adversary wants is to get lucky as per the definition of the prior slide. So what it does is it looks at the first blocks of everything that comes back and says, did I get lucky? Meaning, is it the case that there's 2 choices of I, say j and t, for which those first blocks are equal? So cj0 and ct0 are the same. And that may not happen. It may happen more than once. S collects the set of all pairs for which that equality happens. So these are indexes of the queries under which this equality takes place. If the adversary was unlucky, this set will be empty. There was simply no time where these first blocks were equal. If that's the case, then it can't do anything. It'll just return a 0. So let's say it got lucky. That means that there's some pair for which these 2 things are the same. What that means is we're now in a position to exploit the previous slide. So on that slide, we remember that if you got lucky, so these 2 are equal, testing whether these 2 are equal tests whether the messages are equal or not. So it doesn't matter which pair you use. It can, let's say, pick a pair at random from here, but for simplicity, assume there's just one anyway. So it grabs that one. And then it tests equality of the second blocks of the ciphertext corresponding to these indexes. If those are equal, it tells it that the corresponding messages are equal. But that can only happen in the right game, and so it returns a 1. Okay, so this is our attack. This is perhaps a more interesting or complex attack than many others we've seen. And the effectiveness emerges when we look at how the advantage scales with Q. Q is a parameter, and the adversary picks it differently depending on how much success it wants. So let's do that analysis. So this looks like a busy slide, but a lot of it is just cut and paste. Here I've just replicated the adversary just so that you can look at it again. And here I've just replicated game right. The only change I've made is to specialize it to the encryption scheme we're studying. So whereas in the general case, the left to right procedure would encrypt the right message M1, I do encrypt the right message M1, but I detail the steps specific to counter mode. I pick an initial vector at random, run the block cipher with the key chosen here on 1 plus this value over here. Since we have only a 1 block message, I don't have to bother about more than that, and form the ciphertext by adding this pad to the actual data block. And I return the full ciphertext, which means both this and this. Okay, so nothing happened yet. Now we're going to start asking, what is the probability that our adversary returns 1 when it's in the right world? We look at the code. It returns 1 whenever this equality holds and the set S was non-empty. Okay. However, we are now in the right world, so we know that the messages encrypted is always 0. So regardless of what index we have here, for both J and T, the message is in fact 0. So what is the second block of the ciphertext under the assumption that we got lucky and this set was non-empty so that the first blocks are equal? In the case of the jth message, it's the message we're encrypting as per this, plus the pad, and the pad is this value over here for this ciphertext block here. And similarly for T. However, both cases the message is 0. So now look at these parts. Well, this uses the first block of the ciphertext, but those were the same since we got lucky. What we conclude is that these two are equal. Okay? And you can verify that at your leisure, but what it's telling us is this equality is always true. That doesn't mean we always return 1 because we need that this set is non-empty, but what it tells us is that the probability of returning 1 is exactly the probability that this set is non-empty. Okay, now we need another observation that this probability is something we studied. Remember, the collision probability for throwing cue balls into 2 to the n bins is the probability that if I pick random values from a set of size 2 to the n, then if I do that q times, 2 of them will be the same. That's exactly what we're testing here. These 0th blocks of the ciphertext, as per this, are simply random n-bit strings. So what we're asking here is, are there 2 of them that are the same? And so this probability is just this collision probability. Okay. To determine the advantage, we also want to know what is the probability the adversary returns 1 in the left world. And we're going to argue that it's 0. In the left world, the adversary never returns a 1. Why is that? Again, we've simply shown the same adversary here. We've shown the left game here, almost identical to the right. The only difference is here we have M0 in place of M1 because the left message is being encrypted. If the set here is empty, we certainly return 0. So that's easy. If the set is non-empty, we have to worry that maybe we return a 1. The claim is we don't. Why is that? Because in this case, we did get lucky. So these first blocks of the ciphertext here are equal. Look at how these second blocks are defined. It's through this equation. So they're the message plus this thing over here. And that's what's written over here for the jth block and the tth block. These two being the same means that the result of E sub k on these things is the same. But j and t are not equal. That's because everything here is just incrementing counter values. You never reuse a message. So these two ciphertext blocks are always unequal, and so you will not return a 1. Okay? Again, it takes a little bit of time to walk through all of that, but there's nothing particularly difficult. It's just a bunch of steps and you go through them and conclude that this probability is 0. To get the advantage, we subtract them and we get right minus left. Remember, the right was this collision probability, the left is 0. And so we're left with the collision probability. And now to get a numerical sense of what's going on, we use one of our estimates. From the prior chapter, we had a fact, and it told us that this collision probability grows quadratically in Q and inversely in 2 to the n. And furthermore, we even have a lower bound, which says it's about 30% of Q into Q minus 1 over 2 to the n. And this is where we see kind of the punchline. The punchline is that this starts getting close to 1 when Q starts getting close to the square root of 2 to the n or 2 to the power half of n. And this tells us that counter mode can be broken, at least in this IND-CPA sense, in a number of queries which is proportional to 2 to the power 1/2 of the block length of the block cipher. And what's interesting about this as a conclusion is that it's independent of the cryptanalytic strength of the block cipher. No matter how good was your design and how well your block cipher resisted key recovery attacks, a small block size will increase the effectiveness of this attack. And then you have a violation of privacy. This exercise asks you to extend that attack from 1 block messages to messages of more than 1 block. So let's, before moving on, let's look at some consequences of this and its impact on practice. For DES, the block length is only 64 bits. So 2 to the power n over 2 is 2 to the power 32, and that's a pretty small number. So the attack is quite effective. Now, that was known in theory for a while, but this piece of work was really instrumental in making it clear that this was a practical vulnerability. So what they did is that they used this attack to actually violate privacy of encryption with 64-bit block ciphers like DES or triple DES in protocols like TLS and OpenVPN. And they published this paper, and if you look at what they do, one user is actually CBC, not counter mode. But the same attack, due to the birthday paradox, as they say here, will effectively figure out the XOR of different message blocks. And this is a vulnerability. And the effect from this was that triple DES was actually retired. As we saw somewhat earlier, the National Standards announced the withdrawal of approval for triple DES thanks to these birthday attacks. So you can see that these birthday attacks are pretty powerful and also well understood in practice as being impactful. And you can see further discussion of this. 2 years ago, there's this question of whether triple DES was still considered safe to use. And at that point, someone is saying yes and no, and talking about various kinds of things. And they kind of give a comprehensive answer and eventually get down to the fact that it has a small block size, and that led to this attack that we just saw, and that called for the removal, right? But in some sense, they're right that the real answer is a nuanced yes or no, depending on your usage setting.